Applications of systems of linear equations. All right, so I want to take a look here at some phrases that can be directly translated into algebraic expressions. So here's my list of phrases, the operations and expressions they can be translated into. All right, so let's look at this expression, x plus 2, and let's look at some phrases that we could translate into the expression x plus 2. A number plus 2 would be represented as x plus 2. That would be this first phrase. A would be a number and B would be 2. So a number plus 2. Another way of saying this would be the sum of a number and 2. The sum of a number, which is A, and 2, which is B once again. Yet another way of saying it is a number increased by 2. So we start with the number x and we add to it 2, so a number increased by 2. The next one is a little bit tricky. If we wanted to represent 2 more than a number, 2 more than a number, 2 is B in this case still, and a number is A, so 2 more than a number is actually written as x plus 2, not 2 plus x. And then let's take a look at the next one, which would be the total of a number and 2 would also be translated as x plus 2. And lastly, 2 added to a number. 2 added to a number would also be written as x plus 2. So these are different phrases that translate into x plus 2. Now let's take a look at some phrases that translate into x minus 2. Subtraction. So the first one would be a number minus 2. A number minus 2 is written as x, a number, minus 2. We could also write the difference of a number and 2. This is x minus 2. It's the difference of a number x and 2. We could also say A decreased by B, or a number decreased by 2. A number decreased by 2. And here's the one that's tricky once again. B less than A, or 2 less than a number, is not 2 minus x, it's x minus 2. So be careful if you see 2 less than a number as a phrase that needs to be translated into an expression. 2 less than a number is actually represented as x minus 2. All right, and then we have also 2 subtracted from a number. 2 subtracted from a number is also translated as x minus 2. So all those are phrases that represent x minus 2. All right, now let's take a look at multiplication. Multiplication, 2 times x. 2 times a number is representing 2 times x, 2x. You could also say twice a number. The product of 2 and a number is represented as 2 times x. So 2 times x, the product of 2 and a number. And like I said, 2x can also be said as twice a number. 3x would be 3 times a number, and so forth. Now let's take a look at division. Division. X divided by 2. A number divided by 2 is translated to x over 2. A number divided by 2 is translated as x over 2. The quotient of a number and 2 also translates x over 2, and also the ratio of a number and 2 translates into x over 2. So these are some phrases that translate into division. Also, if you see half of a number, half of a number translates to x over 2, a third of a number translates to x over 3, and so forth. Okay, so you will be directly translating to solve some of these problems, these applications. Now let's take a look at a geometry application of systems of linear equations. Let's take a look at a rectangle. And a rectangle has a length, which is this long side right here, which is also doubled up here. There's a length here and a length here, 2 lengths. And there's a width, which is this short side, which has a counterpart over here also. So there are 2 widths here. So if you were going to go around the perimeter of this rectangle and walk that entire distance, you would walk two L's, this L and this L, and two W's, this W and this W. And that's why the formula for the perimeter of a rectangle, the perimeter of a rectangle is two L's, the top L and the bottom L, and two W's, the side L over here, the left side and the right side, or the right side width and the left side width there. All right, so we have the perimeter of a rectangle given by this formula. We can use that to solve questions that involve the perimeter of a rectangle. For instance, here's an example. The length of a rectangle is 3 feet less than twice the width. The perimeter of the rectangle is 24 feet. Find the dimensions of the rectangle. Well, the dimensions of a rectangle are its length and its width. So we're looking for the length and the width, and it says here that the length of a rectangle, L, we'll call it L, and an is a word that translates into an equal sign. It's the verb to be. So the length of a rectangle means L equals, and then this is an expression that I can translate directly. 3 feet less than twice the width means to subtract 3 feet less, from 2 times the width. So this equation here comes from this first sentence. The length L of a rectangle, L, which is equals, 3 feet less means to subtract 3. It's one of those keywords we could translate from phrases. 3 feet less than 2 times the width. Twice the width is 2 times W. So there we have an equation for the length in terms of the width. The second sentence says that the perimeter of the rectangle is 24 feet. We know that the perimeter P, which is 24, is equal to 2 times the length plus 2 times the width. We got that information previously. So this equation comes from the second sentence telling us that the perimeter P is 24. And then we know that the perimeter is 2 times the length plus 2 times the width. So here we have a system of equations, and we can solve this system of equations by using substitution. I notice that this top equation is an expression for L, the length of the rectangle. I can replace the L in the second equation, the perimeter equation, with 2W minus 3, and that's exactly what I'm going to do. I'm going to have 24 is equal to 2 times 2W minus 3 plus 2W. So 24 is equal to 2 times 2W minus 3, which was L, plus 2W. And then I'm going to solve this equation for the width, W. I'm going to do that by distributing. 2 times 2W is 4W, and 2 times negative 3 is negative 6. So I get 4W minus 6. And then I'm going to combine like terms. 4W plus 2W makes 6W. To solve this is now a two-step equation. To get rid of subtraction of 6, I add 6 to both sides. When I add 6 to both sides, the left side 24 plus 6 is 30. And the right side, the positive and negative 6 cancel, leaving just 6W. Now to get W, all I have to do is divide both sides of the equation by 6. So 30 divided by 6 is 5. And on the right, I just get W. So W is equal to 5. I've found the width of the rectangle. Now to find the length, I can recall that the length is 3 feet less than twice the width. This equation. And then I can just replace the width with the width I've just found of 5. And I get that L is equal to 2 times 5 minus 3, which is 10 minus 3. The length of the rectangle is 7. So there I've found the dimensions of the rectangle. The length of the rectangle is 7. The width of the rectangle is 5. Let's take a look at another geometry application here. And this time we're talking about angles. So two angles with measure x degrees and y degrees, like these angles here, are complementary if x degrees plus y degrees is equal to 90 degrees. So if x plus y equals 90 for those two angles, the measure of the angles in degrees, then these are called complementary angles. There's another type of angle called supplementary angles. Two angles with measure x degrees and y degrees are supplementary if x degrees plus y degrees is equal to 180 degrees, that's a straight angle here. So x plus y makes a straight line. When you add those two angles, we have a straight line here. These are called supplementary angles. So we have complementary angles that add up to 90 degrees. X plus y adds up to 90 degrees, complementary. And we have supplementary angles that add up to 180 degrees. Now let's take a look at an example. Two angles are complementary, which means the measure of the two angles has to be 90. The measure of the larger angle is 3 degrees more than 9 times the measure of the smaller angle. Find the measure of both angles. All right, well, let's see. The first equation, or the first sentence, gives us our first equation. The two angles are complementary, means that if you add the two angles together, you should get 90 degrees. That's one equation. As a second equation, I'll look at this second sentence. The measure of the larger angle, which I'll call y, is, which translates to the equal sign, 3 degrees more than 9 times the measure of the smaller. 3 degrees more means add 3. And what I'm adding 3 to is 9 times the measure of the smaller angle, which is 9 times x. 9 times x. So here I have my system of equations. One equation is the first sentence. The other equation is the second sentence. It wants me to find the measure of both angles, x and y. So I have a system of equations here. To solve it, once again, I'm going to use substitution. I notice the second equation is already solved for y. And I'm going to use that to replace y in the first equation. So instead of y in the first equation, I'm going to have 9x plus 3. So I'm going to replace y with 9x plus 3. And then I'm going to solve for x. X plus 9x makes 10x. So I get 10x plus 3 is equal to 90. I subtract 3 from both sides. This is a two-step problem. And when I subtract 3, I get 10x on the left side is equal to 90 minus 3, 87 on the right side. Then the last step is to divide both sides by 10. So I divide the left side by 10 and I just get x. Divide the right side by 10 and 87 over 10 is equal to 8.7. So the smaller angle is 8.7 degrees. Now we can find the larger angle because I know the two angles have to add up to 90. X plus y has to equal 90. And I know that the smaller angle, x, is 8.7. I can now find the larger angle, y, by subtracting 8.7 from both sides. And I'll get that the y, the larger angle, is 81.3. 81.3. So this is how we do these angle problems with complementary and supplementary angles. All right, the last type of problem I want to look at here is the uniform motion problem. So we have the distance traveled d by an object moving at a rate r for a duration of time t is given by distance d equals rate r times time. D equals rt, distance equals rate times time. So let's take a look at an example with a boat on a river. So a boat travels 896 miles with the current, so you're going downstream in this case, in 32 hours. The return trip, which is going upstream back to where you started, takes 56 hours. Find the rate of the current and the rate of the boat in still water. So it wants to know how fast the boat would be going if it weren't on a river that has a current, and also what the speed of the current is. I'm going to set up a table to do this. In the top of the table, I'm going to have distance, rate, and time, because we know distance is equal to rate times time. That's the relationship between the numbers here. And I'm going to start off with the current. With the current, the boat travels 896 miles in 32 hours. That's a distance and a time. So we'll put those in. The distance of 896 miles and the time of 32 hours. I'll put those in to the row that has with the current, the distance, and the time columns. Now I'm going to go ahead and I'm going to fill out the second row. I see that the return trip, which is going upstream now, takes 56 hours. And since it's a return trip, the distance will be the same. So the distance is 896 because I'm just going back to where I started. But the time is now different because I'm fighting the current. I'm going upstream. So it takes 56 hours in this case. 56 hours. So now I'm going to go ahead and address the rate column. When the boat is going with the current, we're going to take the boat speed B and add it to the current speed C. They're going to be added together because the current is actually pushing the boat along. And then when we're going against the current, the boat speed and the current speed should be subtracted because now the current is actually fighting the boat and the speeds are going to be subtracted. All right, so I have the whole thing figured out here. And I remember the formula that says distance is equal to rate times time. I have here a column of distances, a column of rates, and a column of times. So I'm going to take each row, and each row is going to be an equation. The first row, 896 is the distance, is equal to the rate of B plus C, that's the boat's rate plus the current's rate, multiplied by the time of 32 hours. Then I look at the second row, I have the same kind of equation. 896 is equal to rate, boat speed minus current speed, or boat rate minus current rate, multiplied by 56 hours, which is the time. So I get these two equations. I have now a system of equations that I can solve. Here's my system of equations. I'm going to get rid of the parentheses in both equations by distribution. So 32 times B, 32 times C, 56 times B, 56 times negative C, and I'll get this system of equations that has the same solution as the original. All I did was distribute. And then I'm going to eliminate one of the variables. I'm going to eliminate C, the current speed. So I'm going to use elimination. I'm going to find the least common multiple of 32 and 56, the two coefficients of C. The least common multiple of 32 and 56 is 224. So I'm going to make this into a positive 224 and this one into a negative 224. So the first equation, I'm going to turn this coefficient of C into positive 224 and this coefficient of C into negative 224. And I'm going to do it by multiplying the top equation by 7 because 7 times 32 will be positive 224. And I'm going to multiply the bottom equation by 4 because 4 times negative 56 will be negative 224. So now I'm multiplying the whole top equation by 7, the whole bottom equation by 4, and I get these two equations now. Once you get these two equations, the 224C and the negative 224C will cancel each other out. We're just going to add these two equations together. And when we add them two together, these cancel out. We get 224B plus 224B is 448B. And 6,272 plus 3,584 is 9,856. Now I can find the value of B, which is the speed of the boat in still water, by dividing both sides by 448. When I divide both sides by 448, I get that B is equal to 22. So the boat is going 22 miles per hour in still water. But because the current is on the river, when it's going with the current, it's actually going a little faster. When it's going against the current, it's actually going a little slower. And we can figure out how much faster and how much slower by finding the current speed. So I'm going to take this equation right here. Actually, let me take this top equation, 896 plus 32B plus 32C. And I'm going to plug in 22 for the boat speed and find the current speed, C. So 32 times 22 is 704. And then I subtract 704 from both sides. And that gives me 192 is equal to 32C. When I divide both sides by 32, I get C is equal to 6. Meaning that the current speed is 6. So when I'm going with the current, I'm actually traveling at a speed of 28 miles per hour. The return trip upstream I'm actually fighting the current, and it's going to be 22 minus 6, which is going to be only 16 miles per hour upstream.